In this lesson, we're going to build on our understanding of vectors by looking at how two single forces or vectors can combine to form one new resultant vector. Adding and subtracting vectors is about building a bigger story. How do two different forces acting together move an object? How do you find the result of two different directions of motion? When you add vectors, you're building a path. When you subtract vectors, you're finding the difference between motions. Your goal by the end of this lesson will be able to solve problems involving the addition and subtraction of vectors. So there's two different ways that we can add vectors. The first way that we're going to talk about is this triangle law of addition. And in the triangle law of addition, we're actually adding the vectors tip or head to tail. And we're going to use our trig to find the magnitude and direction of the resultant vector. The triangle's law is good when you chain one movement to another. So, for example, you go one way, then you change direction and you go another way. So, what this would be saying would be if this was vector A and this was some vector B, my resultant vector will be this vector down here, and this will be A plus B. That's my resultant vector. Another method is the parallelogram method, and this places the vectors tail to tail. So they are placed right there, tail to tail. So here's my vector A, and here's my vector B. This is used if the vectors both start at the same point. So if you think about an example that I always like to think is if you have a boat, like a little rowboat that's being pulled by two people that have a rope hooked to the same ropes hooked to the same point on the boat, tied to the same hook, and they're pulling from different directions. So this is what we're talking about. We're talking about 1 point, two vectors. One's being pulled that way, one's being pulled the other way. So what you would do would be to draw both vectors so that they meet tail to tail. They're both starting at 1 point. Then you're going to imagine that you're completing a parallelogram. So you're going to draw lines that copy the vectors to form a four-sided shape. So if I were to imagine that there was another vector A over here and another vector B up here, I've made the square shape, or I've made a parallelogram. The resultant vector will be this vector right here in the middle. So the diagonal of the parallelogram from the starting point to the opposite corner is the sum of these two vectors. This would be A plus B, or my resultant vector. You can think of it as one vector pushing an object northeast and another pushing it southeast at the same time. The object doesn't go fully northeast or southeast, it goes somewhere in the middle, and the parallelogram law shows you exactly where it ends up and how far it goes. So let's take a look at an actual example. So we have two vectors, u and v, and they have a common initial point that form an angle of 60 degrees. So this is our clue right here, this common initial point that's telling me which method I'm going to use to add them. And in this case, if they're both starting at a common point, I'm going to use the parallelogram method because they're both starting at the same point. So we know there's an angle of 60 degrees between them. Vector u has a magnitude of 6 and vector v has a magnitude of 8. So we're being asked to find the resultant vector of u plus v at an angle and the angle between u and v, u plus v and v. So the very first thing that we're going to do is we're going to draw it. So what is this going to look like? Well, I said it's starting at 1 point, and I have vector u that's coming out in this direction, and vector u, remember, has a magnitude of 6. Vector v is coming out at an 60-degree angle from vector u, and vector v has a magnitude of 8. So now I'm going to use my parallelogram, the parallelogram addition. So that means that I am going to create a parallelogram by making imaginary vectors to complete the shape. So this vector here would be equivalent to vector v, and this vector here is equivalent to vector u. Okay, and then my resultant vector comes down the middle, and down the middle will be u plus v. Now, we need an angle. We need this angle right here. And to find that missing angle, we're really just going to use what we know about four-sided figures. And we know that four-sided figures all have a total interior angle of 360 degrees. Well, if this angle is 60 degrees, then this angle will be 60 degrees. So I can subtract 60 degrees twice, or 120. That leaves me with a total remaining amount of angle of 240 degrees. Because these two angles are the same, well, these two angles will be the same, which means I can divide this 240 by 2 to give me the other two interior angles of 120 degrees. So this angle here is 120 degrees. Now, this is simply a trig problem. We're going to use the cosine law to find the magnitude and the sine law to find the direction relative to vector v. So let's start by finding the magnitude. So magnitude. Like I said, we're going to use the cosine law. So u plus v squared, and you'll notice I'm dropping the arrows on top. You can keep drawing them on there. I understand that they're vectors. You understand that they're vectors. So just for simplicity of having to rewrite it multiple times. Okay, so u plus v squared is going to be equal to 6 squared plus 8 squared minus 2 times 6 times 8 times cosine of 120 degrees. When we do all of this math, we end up with u plus v squared is equal to 148, which means that u plus v is going to be equal to the root of 148. And if we take the root of 148, we get an answer of approximately 12.2. So that's our magnitude. Now we need to determine our direction. So I'm going to pop that down over here. So this is our direction. And remember, I said this is our direction relative to v. So we are looking, let me get another color here. We are looking for this angle right here. This is what we're looking for, is that angle right there. So if I want to know the direction of that, I'm going to use my sine law. So sine of my unknown angle over 6, because that is the side that's opposite there. And that will equal sine of 120 all over my u plus v, which in this case was the root of 148. You'll notice I've put the root of 148 back here because I want it to be as exact as possible, so I don't want to lose any decimal places. So I'm going to use the square root of 148 under there instead of the rounded answer from over here. If we rearrange to solve for our angle, we get an angle approximately equal to 25 degrees. So now, because this is a word problem, we need to end it with a statement. So therefore, u plus v, vector u plus vector v, is equal to 12.2 units, whatever those units happen to be. And this is, and it's situated 25 degrees from vector v. Let's look at another question that combines a few of the things that we've been talking about. So I have vector A that equals 2 meters, and its direction is south 30 degrees west. Then I have vector B that equals 3 meters, and it's just at 75 degrees. We're going to assume that that's 75 degrees from north, just because no other information has been given. So now we're being asked to determine 4a minus 2b. Well, 4a just simply means that it's 4 times the length of vector A, and 2b just means it's 2 times the length of vector B, but the negative means that it's in the opposite direction. So let's draw these out just a little bit before we connect them together. So I'm going to draw just a quick little compass rose here. Here's my north, south, east, and west. And I'm going to put this first vector A in there. So vector A has a magnitude of 2 and a direction of south 30 degrees west. So I'm going to start at south and go out 30 degrees west. And that's where my vector A is going to be. So that's 30 degrees. Here's my vector A. Now, the other vector that I have, this b that equals 3 meters and is at 75 degrees. Remember, I said we're going to say it's 75 degrees from north. So that 75 degrees from north, we're going to start at north and go 75 degrees. So here is our vector. Here is our vector b. But we don't want vector b. We want the opposite of vector b. So that is going to be completely in the opposite direction. It's going to have the same magnitude but opposite direction, which means that this angle here now is going to be 75 degrees. They are opposite. So now this is a situation where we would use the triangle method or tip to tail to determine the resultant. So now let's draw these two together and start doing some vector addition. So I'm going to redraw just a little bit of a crosshatched compass rose, north, south, east, west. Now I've got my vector A, but it's not just vector A, it's 4 times vector A at 30 degrees. That means that if it's 4 times A and A is equal to 2, then that means that it will be 8. So I am going to draw at 30 degrees this vector here that is going to be 4A, which equals 8. So 4 times 2 is 8, and this angle here is at 30 degrees. Now we have to add in our opposite vector, our negative b, our opposite vector, and we know that that's at 75 degrees. So here's how I'm handling that. I'm putting a new little compass bit right there, and I'm going to draw it at 75 degrees from the south. So there's 75 degrees. And now it's 2 times b. b was worth 3. I'm actually going to draw that a little bit longer because 2b, negative 2b equals 6. So that's our magnitude for that is 6 meters. Sorry, I do know the units. It's 6 meters. So now our resultant vector will actually be right here. So this resultant vector will be 4 times vector A minus 2 times vector B. And that's what we're trying to find out. In order to be able to figure that out, we need to know what this angle here is. And we can figure that out just by looking at what angles we have. So if this angle here is 30 degrees, then this angle right here is 30 degrees. So I know I have to add 30 degrees. Then we have another 90 degrees. And then I have from here to here, so right here from my westerly line to my vector 2b, negative 2b, I have 15 degrees because 90 minus 75 is 15. So that gives me that angle, that interior angle of 135 degrees. So that is the angle that I'm going to use to solve this question. Just like all the other ones, we're going to find the magnitude using the cosine law and the direction using the sine law. So magnitude. So my magnitude will be 4a minus 2b squared is all equal to 8 squared, because remember that's 4 times a, plus 6 squared, that's 2 times b, minus 2 times 8 times 6 times cosine. Ooh, I'm barely going to squeeze it in, of 135 degrees. Okay, so my magnitude of 4a minus 2b is approximately equal to 12.96 meters. Now I need the direction. Direction will be sine law. So sine theta all over 6. Because the angle that I'm really trying to find then is I'm trying to find this angle here, which is opposite my side 6, because I'm going to use that to determine the total angle. Okay, so sine theta over 6 is equal to sine of 135 degrees all over our new 12.96. So that gives an angle approximately equal to 19 degrees. Now remember, this is this small angle here, but we need it relative to one of our directional points, west or south, we're going to do it from south. We're already 30 degrees out. So 30 degrees plus 19 degrees gives us a total angle of 49 degrees. So we could say, therefore, that 4 times vector A minus 2 times vector B is approximately equal to 12.96 meters, and my direction is south, 49 degrees west. We're going to end this lesson by talking about some rules. So when we add vectors, there are some important rules that always work, just like with regular numbers. The first set of rules that we're going to talk about are the properties of vector addition. So this is the first one that we're going to talk about. So order doesn't matter when we're adding vectors. If I add vector A to vector B, I get the same result as adding B to A. So if we take a look at this, A plus B is the same as B plus A. If I walk 3 steps east and then 4 steps north, or I walk 4 steps north and 3 steps east, I end up in the same place. The other property of vector addition is the associative law. And this one really tells us that it doesn't matter how you group vectors when adding more than 2 of them. So I could have a bracket A plus B and add those together first and then add C. Or I could add B plus C and then add A. The result is the same. Grouping them doesn't change where they end up. So again, if you walked 2 steps north, 3 steps east, and 4 steps north again, you could walk north and north, or east and north, then north. And either way, your final position will be the same. The moral of the story here is that vector addition is flexible. Now, the second property that we're going to look at are the properties of scalar multiplication. When you multiply a vector by a scalar, and a scalar, remember, is just a number, you're changing its length but not its direction, unless the number is negative, and then as we saw, it changes direction. There are 2 important rules for scalar multiplication. The first one is this associative law. So this one here, the associative law. This basically says that I can group scalars however I want when multiplying a vector. So if I have 2 numbers, m and n, multiplied together times some vector a, well, that's the same as multiplying a vector by a number first and then multiplying it by the other number. So if I have m and n, I can multiply those together and then multiply it times the vector. Or I can multiply the vector by one of the 2 numbers and then multiply it by the number. Grouping the numbers differently doesn't change the final vector. We also have something. Oh, no, I skipped a page. We want to continue with this associative law because we didn't finish it. The second rule in that properties of scalar multiplication is my distributive laws. And there actually are 2 versions of this law. So my distributive over, so this first one, the distributive, my cat is like running like crazy. Distributive over vector addition. So all this is saying is that if I have some number times 2 vectors added, it will be the same as multiplying both vectors by that number and then adding them together. So if you add 2 vectors first, then multiply by a number, it's the same as multiplying each vector by the number separately, then adding them together. So if you want to think about it, you can add 2 movements together and then double the result. That's the same as doubling each movement separately and then adding them up. The last part, or the second version of this distributive law, basically says that if you add 2 numbers first, so if I add 2 numbers first and then multiply the vector, it's the same as multiplying them separately and then adding them together. So if I add 2 and 3 to get 5 and then multiply by a vector, it's the same as doing 2 times the vector and 3 times the vector separately and then adding them up. The third thing that we're going to look at here, the third property today, is this idea of the properties of the 0 vector. So we also have something called the 0 vector, and it's written as this 0 with the vector symbol over top of it. The 0 vector has 0 length, so no magnitude and no direction. It's like standing completely still. You didn't go anywhere. So if I add the 0 vector to any other vector, it doesn't change the vector, just like adding a 0. So if I have vector A plus the 0 vector, I still end up just with vector A as my answer. Now here's the important part. For every vector A, there is a negative vector called negative A, and that's what this is showing right here. Negative A has the same length as A, but it points in the opposite direction. So if vector A pointed in this direction, negative A would have the same magnitude, but would be pointing in the opposite direction. When you add a vector and it's negative, you get the 0 vector. So vector A plus the negative vector A, and we get the 0 vector. It's like walking 5 steps east, that would be vector A, and then walking 5 steps west, that's negative vector A. You end up back where you started. There's no movement overall. So in simple terms, the 0 vector means no movement at all. Every vector A has an opposite negative A, or an opposite vector that undoes it, and adding a vector to its opposite cancels it out and gives you the 0 vector. So that's it for this one today. There are lots of practice questions listed, and there will be an exit ticket for today's lesson as well. As always, feel free to email me if you have any questions.